This talk will be given by Davide Paglieri. He just told me how to say it correctly, but I may have butchered it again. He's going to present his work on the paper Adversarial Examples of Multi-Agent Reinforcement Learning with Quality Diversity. And he's currently pursuing his PhD at UCL under supervision of Dr. Tim Rockstashel. So with this, I think I will let David take over. And
yeah. Thank you for the introduction. Yeah. So hi everyone. I'm Davide Paglieri. I'm a UCL. I'm PhD student at UCL, and I will be presenting my joint work with Michael Sanvelian, who's a PhD student at UCL and Meta. Our work is called Multi-Agent Diagnostics for Robustness via Illuminated Diversity, or MADRID. Before we start, like this slide you see here were mostly made by Mika for the AMAS oral where he presented this. So thanks to him for the slides. I made a few, I added a few things here and there, but the slides are mostly made by him. Okay, so let's get started. So what is the motivation of our work? Well, first, let's go through the title again. We're doing multi-agent diagnostics for robustness. So multi-agent systems are getting more and more common in the real world. So if you think about interactions with chatbots, such as LLMs, such as ChatGPT, these are inherently multi-agent interactions, where there is you and then there is the chatbot agent. Similarly, maybe if you think about autonomous driving, like a fleet of autonomous cars, like the image on the right, that is also like a multi-agent system where ideally we might want these cars to be interconnected and communicate with each other. So it's crucial in these situations to be able to assess the robustness of these systems before deploying them in the real world. Obviously, in situations like in the one in the left, it's maybe more important like than other situations, but also if you think about chatbot agents, maybe we don't want them to be brittle to adversarial examples, or like there are plenty of multi-agent systems that can like be exploited in many ways. The way we know that multi-agent reinforcement learning can achieve really good performance on like a variety of tasks. We have like on the left, there is an example like of AlphaStar, where they showed they were able to beat like the best human players in the world in a very, very complex game. But also like more recently, there has been like Gran Turismo, beating the best human players in Gran Turismo and in TiZero, which is a very complex strategy game. However, this multi-agent reinforcement learning method, these multi-agent AI agents are, while they are very good on the tasks that they know very well and that they've been trained on, they often fail spectacularly on out-of-distribution tasks. And there are many reasons for this. This is a general lack of robustness of these AI agents. And this can be because they are overfitting to the training environments, or they are overfitting to the co-player agents like that they've played against during the training. And this is quite common while doing like self-play, but even more advanced self-play techniques like prioritized fictitious self-play often still have these problems. And in the case we maybe want to deploy one like an AI agent in the real world, we want it to be robust with respect to previously unseen environments. So there might be in the real world, there might be infinitely many new scenarios and tasks that might happen, and we also want them to be robust to new unseen co-players that they may face in the real world, hopefully mostly in cooperative scenarios. So it is quite clear that there is a need in multi-agent system to diagnose their robustness before having them deployed in the real world. The solution that we propose is MADRID, or Multi-Agent Diagnostics for Robustness by Illuminated Diversity. And Illuminated Diversity is a fancy way of saying we're using quality diversity, which I will be explaining in a couple of minutes. And the key idea is really that we want to automatically generate diverse adversarial examples where the target policy, which is the policy that we want to deploy somewhere, is behaving suboptimally. So I'll give like a quick introduction to quality diversity framework and how it works. So traditional optimization, usually the goal is to search for a single high-performing solution. While in quality diversity, what we want to do is we want to find a collection of solutions to a given problem. And we want these solutions to be both high-performing and diverse. And what we mean by this, we mean high-performing with respect to their niche, and like diverse so that we have as many different solutions to a given problem as possible. And the most common quality diversity algorithm is called MAPRIDs. And MAPRIDs basically, in order to use MAPRIDs to a given problem, it requires the solutions for the problem to be able to be described using some axes of diversity, as we call them here. So, for example, we can have an archive, and we have feature 1 and feature 2, which may be any 2 given features of the solution we may have. And as long as we can do this, we can describe a solution with on some diversity axis, we can apply MAPRIDs. Other things that are important is like the mutation operator. And the mutation operator, what it does is it basically takes one of the cells in the grid here, and we can do like evolution, like random noise, like many possible ways to do this, but we basically want to somehow mutate this solution in the cell of the grid. And so this solution will end up somewhere else, maybe on the grid, and will be somewhat different. And the third thing that we need is like a fitness function. And the fitness function is basically estimating how good the new solution that we have is, like what's the quality of the solution. And we're always estimating what's the quality of the solution with respect to its niche. So it's cell in the grid. So the way MAPRID works in practice, we initially create new randomized solutions, like new at the beginning, and then in each time step, we select a solution from the archive, we mutate the solution, and then we evaluate it. So we are trying to see what's the fitness like. If the fitness is not good enough to replace the cell in the grid that was previously in the position that describes this solution, we are not adding it. If it's instead good enough, we will be adding it to the archive. And we have this for a number of iterations until we start to fill in like the entire archive. Okay, so let's get to MADRID. MADRID stands for Multi-Agent Diagnostics for Robustness via Illuminated Diversity. And the goal in our project is to diagnose how robust multi-agent policies are using quality diversity. How do we do this? We try to find adversarial examples that have high quality. And by high quality, in the case of adversarial examples, what we mean is the target policy is bad. So the policy that we want to deploy in the real world is is not behaving as well as we hoped in some particular scenario. And diversity, because we want to have find many different adversarial settings that span like a meaningful spectrum of solutions. An important feature of MADRID is that it's a black box approach. We don't need access to the weights or the architecture of these policies. We don't do any gradients, we don't need anything of any of that. We also might use just like an API call to an LLM, and that will also work. And so MADRID is overall a very general method. So the quality of adversarial examples is estimated using regret. And what regret basically is the difference between the optimal policy, the utility of the optimal policy, and the target policy. So the policy that we want to deploy at some point. And obviously, we don't have the optimal policy. The optimal policy in very few cases exists. So what we do is we estimate the optimal policy with a collection of suboptimal reference policies. And basically, instead of actually estimating the true regret, we are estimating a lower bound on the true regret. We apply MADRID, as the name suggests, to football and to Google Research Football. Google Research Football is an open source football simulator. Football in itself is a 2-team zero-sum game. It's 11 players we are actually only controlling 20 of the agents because 2 of the agents, the goalkeepers, are heuristics based. It features both cooperative and competitive dynamics, and it is a very challenging game, Google Research Football, like football in general. The reason for it is it has very long game horizon. In the original challenge of Google Research Football, the reward is very sparse. You only have reward for scoring and for getting scores, so -1 and +1. There is also very large action and observation space, and like the actions are actions like walking, running, sprinting, passing the ball, kicking the ball, cross, or like tackling the opponents, or like sliding, and so on. There are so many actions, and also the observation space is quite large because there are in total 22 players, and so each agent, so each player has observations of its position on the field, its movement on the field, the position of the ball, and the position of the other players, and like movement of the other players and the ball itself. So it's a quite large observation space. The environment of Google Research Football is also stochastic, meaning that given the same scenario, for example, if there is a player in front of the goal, shooting in the same direction shooting the ball in the same direction will not always result in the same outcome. So sometimes it will score, sometimes it will miss, just like in real football. And Google Research Football is one of the most complex environments for multi-agent RL. And there are many toy versions that are often frequently used instead of it. And a very common approach to do it, like to play good, like for research methods to do research, Google Research Football, is to do behavioral cloning from single agent policies. The state of the art at the time we did MADRID, I think might still be the state of the art now, I'm not sure, is TiZero. TiZero at the time significantly outperformed any of the existing Google Research Football agents. The way it worked was it did a curriculum of environments, and this curriculum was quite handcrafted. It had various scenarios from easy scenarios with fewer players in easy positions to the full game, all the way to the full game. And it uses a combination between self-play and PFSP, so prioritized fictitious self-play. And it does a significant amount of reward shaping. As I said, like originally the game of Google Research Football only has reward for scoring and getting scored. But what they do instead, since it does a very complex, like a very sparse reward, they make the reward more continuous. Like they improve the reward by adding a reward for holding the ball, for passing the ball to like teammates, and also they have penalties such as they don't want the players to group together, but they also have other things such as they want the players to move towards the opponent goal and so on. They do parameter sharing, meaning that each player on the team has the same policy, the same weights. And it's trained for 45 days in a cluster with 800 CPUs. So that's a lot of compute to train this policy. But at the time, it was state of the art, and by a significant margin compared to the previous entries. And they claimed in this paper, they had mastered the game of Google Research Football. And while they do definitely very well, probably it wasn't quite mastered yet. And like while looking at TiZero playing, we figured out that there were some weaknesses, and we wanted to try to find if we could exploit or like we could find systematically all of these weaknesses. So that's what we aim to do in our project. So in order to apply MADRID to Google Research Football, we have to identify like the axis of diversity to apply Map Elite to Google Research Football. And the axis of diversity is like the one axis is the environment, so the level. We can procedurally generate the levels, and by what we mean by level is the X and Y coordinates of the players and the ball itself. And by having this, we can have like a meaningfully diverse gameplay scenarios. Another axis of diversity is the opponent policy. So we have the target policy, which is the final Google like TiZero policy, like the TiZero itself. But then we have other opponent policies, which are the built-in heuristics AI that come with Google Research Football, are easy, medium, and hard bots. And we have other agents as well. So we are using 48 checkpoints throughout TiZero's training. So we were given the checkpoints by the authors of TiZero, and we use them as opponent policies. So we can imagine to apply MADRID to Google Research Football, we can discretize the the football field in some X and Y coordinates. So we can have X coordinates of the ball and Y coordinates of the ball has some features in the archive. And as a third feature, we have the opponent policy. And the opponent policy is either one of the TiZero checkpoints or the built-in AI agents. And the way we measure the quality of a solution is by using regret. In particular, what we do is regret is we have the difference between the cross-play and the self-play values between the reference and the target policy. In what ends up happening is, for example, we assign a score like on this value, we assign a quality of 1 if the first policy scores, a quality of 0 if no one scores, and a quality of -1 if the policy B scores. And since Google Research Football is a stochastic game, we do this multiple times to average out any stochasticity. So let's get to a figure to explain better how MADRID works. We have we first select a level in the a level in the archive, and the level again is the position of the ball, the position of the players, and the policy itself, the reference policy. Then we perturb the level only, and we perturb it by adding Gaussian noise to the position of the ball and the position of the players. Then we evaluate how good this new solution is, so how good this level is, by doing the estimating the regret. And finally, if the regret is better than the regret there previously was in the cell where we are adding this new level, or maybe there was no regret at all, we add it in the grid.
David.
So, yeah.
Sorry, can I ask a question? I'm a bit confused. The difference between the reference policy and the target policy. In this case, the reference policy would be the one from the TiZero or other checkpoints?
The reference policy is one of the checkpoints of TiZero or one of the heuristics bots. So it's like it's a weaker policy. The idea is, ideally, we would want to have the optimal policy, but since we don't have that, we are using instead this collection of policies. And the interesting thing is that each of these policies that we are using is weaker than TiZero on the full game. So TiZero is much better than all of these. But still, even having weaker policy, we, as I should show you later, we found many adversarial examples in which the weaker policy was exploiting the better policy of TiZero. So let's get to some results. So we use some baselines. So we have MADRID. As I said, MADRID uses an archive of diverse high regret settings. So we are storing these solutions in an archive. And at each time step, we sample high regret settings from the archive and use them as a kind of a stepping stone to evolve a new solution that we will put then again in the archive. And we use 2 baselines. The first baseline is we call targeted baseline, and we use the archive just like in MADRID. However, at each time step, we generate the levels randomly. So we are not using these stepping stones. And the third baseline is completely random. What we do is we don't archive solutions, and at each time step, we generate levels randomly just to see how likely we are to have to encounter any adversarial example just by randomly finding solutions. And on the right, you can see the regret that we get by, and on the x-axis, the iteration. So we see that the random baseline is actually negative value. So it's regret is less than 0. And the reason for this is that TiZero is a better policy on the overall game than the weaker policy. So if we randomly choose a scenario, it will be more likely that TiZero will win against the weaker policy. The targeted baseline already gets a good results, good score, and MADRID is even better. So on the left here, you can see the scoring rate. So how many goals per game, per scenario, are usually scored you can see again, random baseline, TiZero is scoring against the reference policy more often than the reference policy is scoring against TiZero. The target baseline is already doing quite well, but MADRID is doing even better. So we see that they are scoring at the end of 5,000 iteration. MADRID is finding adversarial examples with scoring rates of almost 70%. On the right, you can see the reference agents on the x-axis. So the policy that's being used to find exploits to MADRID. And on the y-axis, you can see the scoring rate. So it's quite interesting to see how this evolves. So we have the checkpoints from 1 to 48, and the bots, hard, medium, and easy bot on the left. So what happens with MADRID is we start with a archive that we, as MapElites, like as it worked with MapElites, we slowly fill this archive with more and more like qualitatively good solutions, which in this case is adversarial examples. So let's get to some quantitative results of MADRID. There are a lot of quantitative results, like which shows how diverse like these adversarial scenarios that are found are. One of which is like better passing. We found often TiZero was making suboptimal decisions while passing the ball. So here TiZero is doesn't understand that it could pass the ball to a better opponent, to a better teammate, sorry, and instead tries to score, while the reference policy from the same position passes the ball to a better opponent, like to a better teammate who scores. So this is the example that like was quite fast, sorry. TiZero tries to score and it fails, and the reference policy actually passes the ball and it scores. And the reference policy, as I said, again, it's interesting to know that it's weaker on the full game, but in this particular scenario is outperforming TiZero. Another very interesting result was offside. We found that, especially towards the beginning of training, the archive had many offside scenarios. And the reason for this is that it's very easy to get an offside. Like you just need to pass the ball like further than the penultimate opponent towards the goalkeeper. And here we see like TiZero is passing the ball towards one of his teammates, which is an offside, while the reference policy just runs towards the goal and goes to score. So here TiZero passing the ball and it's offside, and the reference policy just runs all the way and like scores. A few other ones, we have positioning, where like TiZero shoots from not great position on the field, while the reference policy finds a better angle and scores. Then we have own goals, which is another very interesting one. We found that TiZero was scoring in its own goal for no apparent reason. It was just shooting against its own goal in some scenarios, and it's not very clear what triggered this behavior, but it happened quite a few times. And on the same scenario, the opponent, like the reference policy, manages to go to score quite quickly. So we also have other, like, there is a variety of these examples. We have better defense, where one of TiZero's defenders doesn't understand that it needs to go and help the goalkeeper and cover like the ball, and the reference policy does. So here TiZero fails on the left and the opponent scores, and on the right the defender goes to tackle the ball, and this is again the weaker policy. Finally, last one I'm showing is another weird confused behavior of TiZero on the left. You can see it takes the player takes the ball and just keeps running up and down the field, and does that actually for quite a lot of time. And somehow the opponents don't even manage to get the ball, while the reference policy from the same position passes the ball forward and goes to score. So some of you may be asking, like, we have adversarial examples now, and now what? Can we somehow improve and like robustify the target policy with these examples? And the answer is yes. This is something that we planned on doing for Google Research Football. However, we ran in time issues. We had to submit the paper to AMAS, but Mika, who like my co-author, together with like the team at Meta, used improved MADRID and used a version very similar to MADRID, which they call rainbow teaming, to find adversarial examples to large language models. So they were finding adversarial prompts. They were tricking large language models into outputting unsafe answers. And so what they did then, they used these unsafe answers or like unsafe prompts that were triggering unsafe responses to perform a supervised fine-tuning on the model. And they showed that they could lower the attack success rates on the fine-tuned model using these adversarial examples. So this shows how this method can be applied to like robustify policies. So in summary, I may have gone quite a bit fast, but I hope it's not a problem. I've talked quite fast, yeah. So as a summary, we introduced MADRID, which is a novel black box approach for finding diverse adversarial scenarios to multi-agent policies. And we applied specifically MADRID to Google Research Football by targeting the state-of-the-art TiZero agent to generate a broad set of adversarial examples. However, as we've shown, like MADRID is quite a general method and can be applied with some modifications to many other settings, such as LLMs, but possibly many more as well. And what we also done, we've analyzed the generated scenarios and discovered 11 vulnerabilities of TiZero's tactical decision-making. You can find more scenarios, like more videos of some adversarial examples on the website here, and you can find the archive, like the paper on archive as well here. Yeah, that was it. And I went a bit fast, I realized, but yeah, thank you for inviting me to like this reading group. And yeah, if you have any questions, I'm happy to answer.
Sure. Thanks for presenting. Maybe one thing I maybe wanted to ask was, so I think in this case you used one agent, TiZero agent. Could it be possible if we have a bunch of different policies? Different policies may have different specialities, and we come up with, in some way, since we know the adversarial scenarios for each of them, could we come up with a policy that's kind of an ensemble of those policies using this kind of an approach?
Yeah, I guess that is possible. Like what you could do is you could add maybe a fourth axis on the MADRID grid. Also being careful, because if you add too many axes, then the computation scale up exponentially with every axis you add. But yeah, I think that is definitely something possible. So in case of TiZero, all the 11 players have the same policy, so it's not really applicable there. But you could maybe get like different players from the reference policies and use those policies instead, and like have different agents in the same team. Or yeah, that could be definitely possible.
Okay, thanks. I saw a hand raised. Please unmute your mic and you can ask the question.
Yeah, you did already. It was also my question, because the problem is very interesting, and I thought usually in football you have like different, on soccer, different positions, and then you would say why they don't use different policies for different positions, because right now then a position in attack position needs to learn how to make a goal, and maybe defense player is with a different task, and therefore I thought also with different reward shaping you would maybe get better results with different policies.
Yeah, that is definitely possible. Again, I think a way that you could do this would be by adding, possibly by adding like a fourth axis onto the solution and have it in it like the different players you're using. So you could have like 1 to 11, like the number of players, like the different players. So you could change each player. Maybe it could be a player from a reference policy or from another training that you're doing. Maybe you're training like multiple agents all at once, or like in case you had already a policy, like instead of TiZero, you had something that already has 11 different like agents, like so each with their own weights. I guess you, as like a mutation operator, what you could do then is you could remove one of the players, one of the agent players, and add instead another player in its position. Or maybe you could like also remove half of the team and like change it with other players instead. So there are lots of possibilities in that scenario, in that regard. Yeah.
Maybe another thing that I was wondering was, I think you mentioned the TiZero. I think it was trained for 40 days or something. Was it for TiZero or uh, was it for something else? I'm not sure what you mentioned there. But my question was, how long does it take to finish the diagnostics for this example, GRF example?
I don't quite remember the exact time. We had probably on the paper how much GPUs we've used. I think we have the paper. The GPUs we use were V100s. So the experiments are conducted in-house cluster, the cluster they use at Meta, like Tesla V100s, and each experiment was run with a Tesla V100 and 10 CPUs for each of the 51 reference policies. And each run lasts for 8.5 days for 5,000 iterations. So this is one V100s. I think they were like 16 gigabyte V100s and 10 CPUs. So it's not too intensive.
Was there a reason you went for GRF? Was there any particular reason you went for it, or you might have gone for something cheaper just to come up with results?
I think we went for GRF because it's a very challenging task. Like at the beginning, we were also like we were looking at this project in two ways. One, the idea was just finding adversarial examples to this TiZero state of the art, because we immediately saw while it was good, it was far from really having mastered the game of football. And the question was, how can we actually prove that it's not mastered football? It's not like if you watch TiZero play, you can see it's not playing as top human players would. And maybe it's better. I would doubt that it is, but that was one of the things that we wanted to try. But then we realized like Google Research Football, it is if you optimize it well, it can be quite fast. It's not maybe like the fastest because you cannot run in on GPU because it's like not vectorized on JAX. But yeah, it was still relatively fast enough, I would say, to perform these experiments.
I see. We have a few more questions on the chat. I will maybe read them out. There was one from. Okay, there was one from Cheng Wong. How to measure whether the examples are adversarial?
Yeah, I'll go back on the slides. Yeah, we use basically regret to do this. Regret is a metric. I'll go back to a slide that talks about regret actually. Yeah, regret is basically a metric that is telling us the difference in utility between the optimal policy and the target policy. Again, since we don't have the optimal policy to deploy, we are using, instead of it, a collection of suboptimal, we call reference policies. And we are basically, what we're doing we are estimating a lower bound on the true regret. So we are basically playing, we're doing two things. We are playing, I'm going to on the other slide. Where is it? The first playing TiZero against the reference policy. Like for example, you see here, move this, okay. You see here on the first one, we are playing the reference policy against TiZero from a particular level theta, and we are also then playing TiZero against itself on the same level. So we are estimating this regret by doing the difference in value between crossplay and self-play, and this allows us from the same exact level, and this allows us to know if the crossplay, so the reference policy in that specific scenario, behaved better than how TiZero, so the target policy, does. And we are assigning the score in this way here. So given this value, we assign a score of 1 if the first policy scores, and a score of 0 if nobody scores, and a score of -1 if the second policy scores. So in practice, what ends up happening is if the first policy, if the reference policy scores against TiZero, we already have a score of 1. And then in the second one, if like an additional like scenario, if the second TiZero, like the second policy, so the opponent team actually scored against the first one, we have a score of -1, and we have the highest possible regret in this case, which is 2. I hope that clarifies it.
Yeah, sure. Cheng, if you have a follow-up, you can maybe text again. There is another question in the chat from Lorena. The question is, how do agents handle sparse rewards and long time horizons between rewards?
I think this is more like a question for because what we are doing is we are not using rewards, like where we calculate the regret by seeing who scores and who doesn't. So we have a fixed timeline. I think we have like, I don't remember how many time steps we wait, but we basically, after having initialized the level, we wait for us a certain, probably it's written in the paper exactly, but how many steps we run the game from that point, and we see if somebody scores or not. So we don't let the full game to be like played. Otherwise, it will end up in new scenarios and it will not be the original level anymore. I don't know if that was the question or not. Okay.
Yeah, I think you answered it. Is there any other questions? So if not, maybe we can call this a meeting. Thank you, David, for presenting the paper. It's really good. It was really nice to see your work. And oh, there's one question from Savina. You can unmute yourself if you can. Oh, sorry, that was by, she's saying that was by accident. Okay, well, she was trying to clap. All right. So thank you for presenting, and maybe we can call this a meeting then. Thank you.
Yeah, sounds
Thank
good.
you for
Thank you
joining.
for inviting me, and it was a pleasure.
Cheers.
Bye.
Bye.